Hello, everyone. Today we are dealing with three important calc theorems. Theorems just means like a rule in math that has been proven and we can rely on to do other problems. So there are three of them that are going to pop up in this class. We've kind of been hinting at one of them. The other two are fairly obvious, but they come up when we're trying to justify answers or explain why certain answers exist. So you got to be familiar with them. I'll sprinkle them in throughout the rest of the course. Your discussion asks you about these three theorems, so let's get to it. The first one is pretty much the most basic one, I think. It's called the intermediate value theorem. Intermediate value theorem. All right, so I'm going to give you an example. I'm not going to write it all down. I'll just give you like my bullet point of on the 40, score a TD. So let's say, I'm doing football analogies. You can do whatever you want, but let's say I'm on the 40-yard line of a football field and I want to score a touchdown. Do I have to cross the 20-yard line? I mean, if you think about it, yes, we have to cross the 20-yard line. We have to hit all the values between the 40-yard line and the touchdown. If we're going to go from the 40-yard line to the touchdown end zone, we have to cross everything in between. The intermediate value theorem basically guarantees that you have to hit all the values in between two values. So if I'm on the 40 and I want to score a touchdown, I have to hit the 20. So a more mathematical way of thinking about this is, and we'll keep it with specific examples for now. If you have some function and you know f of 1 equals 4 and f of 3 equals 6, does the function ever equal 5? Well, if you're at 4, you could kind of sketch it out here, which I will. If you're at the coordinate 1, 4, which is right here, 1, 2, 3, 4, and you know 3, 6 is a coordinate, do you have to cross this line basically? Does the function ever have to equal 5? Yeah, if you play connect the dots and you want to get there from one to the other, you have to cross. There it was right there. That's the spot where the function equaled 5. Now, I'm going to back this up. You could cheat and be like, no, it doesn't have to. Watch, ready? Here. There you go, didn't cross. Intermediate value theorem failed. Well, that's your first condition of when the intermediate value theorem applies. The function has to be continuous. So that's one of those conditions. So a lot of times we'll have to establish that the function is continuous, and then we can invoke the intermediate value theorem. Okay, so the function has to be continuous. The other question I asked, does the function have to be, continuous. Does the function have to be differentiable? Meaning, can there be pointy parts? Does that mess everything up? Well, if I had this point here, if you play connect the dots, even if you create a cusp, one of those pointy points of non-differentiability, doesn't matter. Even though this is not differentiable, the intermediate value theorem still applies. So the only condition is the function has to be continuous. It does not have to be differentiable. It can have cusps, okay? So that's the intermediate value theorem. I asked you one of the problems on the homework. I think about that, and you'll kind of see how that works. The second one, the other big one, so really there's two big ones, and then the third one's kind of pops up here and there, is called the mean value theorem. The MVT. So here's my example of the mean value theorem. If I averaged 40 miles per hour driving to work, was I ever going exactly 40 miles per hour? So think about what I'm telling you. I have an average rate of change of 40. If I told you on average I drove 40 miles per hour to work today, does that mean there was ever an instant I was actually going 40? Well, if you think about, well, maybe sometimes you're driving 20 and other times you're driving 60. That's fine. That's true. I could have been driving 20 most of the time and 60 the other half. But at some point, didn't I have to go from 20 to 60? It's that whole acceleration question I asked you. It's also kind of an application of the intermediate value theorem. The answer is yes. I had to have been going 40 at some point. So this is what you'll hear me say about the mean value theorem in the future. You'll hear me say it is the idea that the AROC equals the IROC somewhere in the interval. This has to be true. If you have a function where you find the average rate of change, the derivative has to equal that average rate of change somewhere in the interval. And I've been giving you a couple of these in the performance test. I think I gave you one today. I don't remember. But if I give you an example of what this looks like, I can show you. So here's an example. This is the one that you'll see going forward. So if I give you a function over the interval 0 to 3, find where the average rate of change equals the instantaneous rate of change in this interval. Okay, so first thing you should do is find the average rate of change. That is f of 3 minus f of 0 over 3 minus 0, which is 9 over 3, which is 3. So the average rate of change is 3. We've already talked about average rate of change. That means sometimes it's changing at a slower rate, sometimes it's changing at a faster rate, but the average rate of change is 3. But let's find when the IROC equals this. So first thing you should do is take the derivative, which is 2x, and then you should plug in, well, no, don't plug in 3. I want to know when the derivative equals 3. So this is where you set them equal to each other. And in this problem, it's saying right at the halfway point. How convenient. Doesn't usually work that nicely. But at this x value, this is where the AROC equaled the IROC. In other words, this is like the instant I'm driving to work and my average equaled, or my instantaneous rate of change equaled how fast I was actually going, or the average. Let me say that again. At x equals 1.5, this is the instant where my speed at that instant, my rate of change at that instant, was equal to my average rate of change. So if I show you what I'm talking about on Desmos, we have y equals x squared. So using that cool trick from last time, I can create a movable tangent line. We know that the derivative was 2x. Y minus b equals the slope times x minus a. Create a movable point. So you're telling me that in this interval from 0 to 3, so I'm going to zoom right in on this interval, 0 to 3. If I created a secant line from 0 to 3, which I'm also going to do, y equals, the average rate of change was 3x. So from 0 to 3, there's my average rate of change. Line, secant line. So there's got to be some point where the derivative or tangent line matches up with that. And according to the work we just did, it happened right there, right at 1.5. And you see how the tangent line and secant line are parallel? That's showing that at that instant, at the 1.5 mark, the average rate of change was equal to the instantaneous rate of change. My average, the blue secant line, had the same rate of change as my tangent line. Okay, so the mean value theorem, to sum it up, just says that the AROC equals the IROC somewhere in the interval because of the mean value theorem. Now, what conditions are true for this one? Does it have to be continuous? Yes. Same as the last problem. I could just create jumps all over the place and everything falls apart. So you're going to see that all of these have to be continuous. But what about the other condition, differentiable? Well, if I gave you this problem and had some function with a pointy part in it, like the absolute value, and I had you find the average rate of change from this point to this point. That AROC is 0. But does the derivative ever equal 0? No, look, the derivative is -1 on this entire stretch and 1 on this entire stretch. So the derivative never equaled 0. So we've broken the mean value theorem, because the mean value theorem says there has to be somewhere where if I take the average rate of change over an interval, the derivative has to equal that. But this breaks it. So in other words, the function has to be differentiable in order for the mean value theorem to apply. So a function has to be continuous, has to be differentiable for the mean value theorem to apply. Both are conditions. Okay, and then the last theorem is the one that comes up the least, but it'll be useful for problems we do second semester a lot more. It's called the extreme value theorem. Extreme value theorem. We're going to get into some of these ideas coming up, and then we hit them a lot harder second semester. Extreme value theorem basically says there is a highest point and lowest point in a function. There has to be a max, there has to be a min. There has to be the highest point and the lowest point. Doesn't matter what, in an interval, by the way, in an interval. So you can't just say, oh, from -infinity to infinity, that's not true. No, in an interval, there has to be an enclosed interval. So let's say from here to here, no matter how you draw a function, there's a highest point, it happened to be right here, and there was a lowest point. And I tried to draw it where all of these are kind of the same, but that would be that's the lowest value. Right here was the lowest value. Right here is the highest value. So there's a highest point and a lowest point, otherwise known as maximums and minimums. So there's an absolute maximum and absolute minimum. So that's the other big thing that's going to come up more later. Absolute max and absolute min exist. Has to be. Now, what conditions? You could do the same logic of graphing it out and seeing, but if you tried to cheat and make it not continuous, you could have an asymptote right in the middle, and then obviously it would just keep going up and up and up and up. So no, the function has to be continuous. Has to be continuous. But does not have to be differentiable. You could have cusp, that's fine. As long as the function's continuous, there's always going to be an absolute max and an absolute min in the interval. Has to be. Doesn't matter how you draw it. Okay, so those are your 3 theorems. You just have to have them in your back pocket to justify things. We'll be doing a lot more later. But I do ask you a couple of these types of problems where I want you to find where the AROC equals the IROC, and you'll just do it like I did here. You'll find the AROC, find the derivative, set them equal, solve. And that's a pretty important problem. AP Test loves those. All right, that's it.